A change of seasons means adventures in rain, shine, mist, or snow, or all of the above on the same day. This season, prepare for every season with the Allbirds Mizzle collection. With all-condition traction and materials and features to keep you comfy and dry no matter what, you'll be ready for anything. Go to allbirds.com and use code FRESHSOCKS for a free pair of socks with your purchase. ALLBIRDS.com, code FRESHSOCKS.
Hello, Saver. Whether you're saving for that trip to the tropics or saving for an emergency, now is the time to take advantage of Wells Fargo's savings options. Wells Fargo offers savings accounts that can help you save towards your goals. So, what are you saving for? Visit a Wells Fargo branch or wellsfargo.com/save to open a savings account today.
Wells Fargo Bank, N.A., member FDIC.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again. Thank you for joining us here on the Space Nuts podcast. My name is Andrew Dunkley, and joining me, as always, my partner in crime and all things space and space science and astronomy and astrophysics and genealogy. No, not that. Fred Watson. Hello, Fred.
We'll do genealogy as well. The only thing we don't do, Andrew, is sport and relationships. Everything else is fair game.
Yeah, or politics, maybe occasionally.
We should stay. You're right. We should steer clear of that too.
Definitely should. Now, on this episode 241 of the Space Nuts podcast, we are going to look at the successful landing of the Perseverance Rover on Mars and what happens next. What's it doing? Has it stopped for fuel? Do the kids need to go to the toilet? Things like that. And evidence of life. They might have a go at that. There's also a study into binary stars that's released some results. This is done through the Gaia Observatory, and some of the information that's come out of that's been quite fascinating. So we'll look at that. And questions. This audio question from Judd in Melbourne fascinates me. He's been down watching the tennis, the Australian Open, and he was wondering about the shadows on the court. So, yeah, that's going to be interesting. And another question about the Lagrange points or the Lagrange points, and plenty more that'll probably pop up during the course of our conversation today. But Fred, that 7 minutes of terror, or whatever it turned out to be nothing at all. And the footage of the rover from the landing craft lowering it down and from the rover looking up, spectacular stuff. Taking nothing away from the other two missions that are orbiting Mars at the moment from China and the UAE. This technological achievement takes it to a whole new level. Wow, what an amazing effort to get that thing down. A soft landing on Mars, and all systems go. That's
absolutely right, Andrew. Did you watch it live? I watched the NASA webcast. Did you see that?
I didn't. It was a bit past my bedtime.
It wasn't. It was 10 to 8 in the morning.
Yeah, that's way past my bedtime. No, I didn't know what time it was, and I would have been on the radio at that time.
That's right. Yes, in fact, I remember thinking that. Andrew won't be listening.
Yeah, so I missed it, but I caught it all again later. Yeah, and and it was all over the news. It was just fabulous, and to think that they've dropped that rover down and it's completely made of spare parts.
Yes,
some of it from my Honda Jazz. It's fabulous effort.
So that's where the reversing camera came from, is it? Which is what we have got. Yeah,
that's right.
It was. Just watching it live was fantastic. I was very cheered by all the cheering, in particular because that's a room that I've been in, where the actual mission control is, and you might have been there as well in the Jet Propulsion Laboratory. There's a room which is very familiar. When you've been there and you look at it and see them all doing their clapping and everything, yes, I've been there. But that, of course, a minor detail. But you're absolutely right. It's a total triumph, and I endorse what you just said. That's 3 out of 3 for the 3 spacecraft that have gone to Mars. They've all done what they're supposed to have done. Hope is in orbit, and I think ramping up to its its science mission on the weather and atmosphere of Mars. Tianwen-1 is in orbit. It's going to track down. It's going to start its all the orbital reconnaissance and things that it wants to do to look for the best site to put their lander down, which will be May or June, we believe. But all going well with that. And of course, Perseverance, they really stole the show by not going into orbit, but doing that 7 minutes of terror entry into Mars's atmosphere, and then showing us the video, as you said. So we've got cameras, or the cameras on various bits of the spacecraft that were actually, allowing us to see, not in real time, but a bit later, this footage. I think the 4 cameras involved were the parachute up-look cameras, the descent stage down-look cameras, the rover up-look camera, and the rover down-look camera. So all of those. I
think did I read correctly? It's got 10 cameras on it, that rover?
I think it's 19. It's
19?
A huge number, yeah.
Wow.
Which is why your Honda Jazz doesn't have one.
No, it's got nothing.
Yeah, they've all gone. No, it's that's right. So it's festooned with cameras, and they're pretty high res cameras as well. So we will see Mars as we've never seen it. We probably see lots of 3D images. So we'll all have to get our 3D glasses out to have a look at them. But I think we're in for a treat when this rover starts working. And of course, the other component, Ingenuity, the helicopter, which is currently strapped onto the underbelly of Perseverance, I think inside a dust cover, that I think is going to be 1 to 2 months before it's deployed. And at present, what they're doing is in stages, they're charging up its batteries from Perseverance itself. It was sent there with no charge in the batteries, probably for good reason, I'm sure. But they're charging it up. But apparently, all its telemetry checks out. It talks to the modules and Perseverance that it's supposed to, and all looking good. So far, with these 3 missions, we've got A-OK all the way down the list.
Now, one of the things that NASA has released is audio from just after the landing of Perseverance, and they caught some breeze. Now, I'm going to try and play it, but it's a very, very soft sound. I'm going to play. They sent 2 pieces of audio, one with the rover audio filtered out, but I think I'll leave that in so that you can hear something. But listen for the gusts of breeze that are in the background of this audio. This is Perseverance on the ground. Very hard to hear. There it is.
Yeah, you can hear them there, that little rumble.
Yeah, just a little wisp of breeze from the Martian surface hitting the microphones. Yeah, fabulous. So that's, and the rover, it sounds like my Honda Jazz. So it's in good condition. Very good condition.
And the icing on the cake, of course, is that NASA's Mars Reconnaissance Orbiter has a camera on board, HiRISE, the high-resolution imaging camera that we've talked about a lot because it's picked out the most incredible details on the Martian surface. It sent us back a picture of Perseverance on the ground, the descent stage some 0.5 kilometre away, and the parachute and the back shell a little bit further away again. So the whole of that landing site has already been imaged by HiRISE. I'm sure that was not an accident. I'm sure the orbital parameters of HiRISE of Mars Reconnaissance Orbiter were tweaked so that it would very quickly overfly the landing site. It's great stuff.
Now, that descent stage that had the 4 burners, that it just looked like something out of a science fiction film as it came down. Is it finished now? Has it done its job? Is it just going to be set aside and left to rust?
Yeah. Well, given Mars's zero humidity, it'll probably take a while to rust, although things do go rusty on Mars. That's why it's red. But no, you're right. In fact, it's probably not in good shape because I think once it had done its job, it was just allowed essentially to crash on the surface. There was no thought of controlling it and bringing it down to use it again or anything like that. And in fact, the HiRISE image of the descent stage landing site seems to show quite a dark area that suggests that it's disturbed the soil, it's come down with a bang, and might even be a bit of a crater there. It won't have come down very fast, it'll just be a few meters per second, but it'll be enough for it not to survive as a working piece of kit, and in fact its job is finished, so
yes,
fine.
It did a marvellous job though.
Perfect.
When you think about how they put things on Mars in previous missions, that's a pretty impressive and spectacular way of doing it. Of course, now as they warm up the machinery and charge the batteries and get ready to deploy that helicopter, the search for past life begins.
Exactly, that's what it's all about. I mean, it's geology, but geology very much with a view to trying to find things like microbial mats, the stromatolites that we find on Earth. And the other great thing about Perseverance that makes it quite different from any of its predecessors, although I think this is also going to happen with the Tianwen-1 lander. The idea is to find samples that you really would like to test on Earth because they're so interesting and so fascinating and so promising in terms of them containing signs of past life that they have these containers on board Perseverance into which these promising samples can be put, the lid screwed on, and these things parked on the surface for pick up by a later mission, which is currently in the planning stage. So maybe could even be 10 years' time, but it's certainly something to look forward to. As I said, I think Tianwen-1 has the same sort of plan to provide these little caches of material that can eventually be brought back and analysed on sterile laboratories on Earth.
So what are the odds? What are the odds of them finding something that would suggest there's been life in the past on Mars? And I'm going to assume, based on the way this is being done, we're not going to find anything alive, if there is anything alive on Mars.
There's one of the senior mission scientists, this is a lovely quote from him. He said it's really designed to look for ancient life. It probably would not detect present life unless something actually got up and jumped in front of the cameras. So, that's the level. It's really all about looking for that ancient geological life. And to be honest, and because I've said this before, Andrew, I'm not a betting man by any means, but I think the odds are good. NASA has chosen a really good place to put the rover down. It's the Jezero crater, which has this river delta flowing into it. So there's a river that's flown, it's made a break in the crater wall, and water has flowed gently into the interior of the crater and made this delta quite a large geological feature. If it's anything like deltas on Earth, that will have brought down the silt from all the way down the river and gently deposited it on the floor of the crater. And that might well be where you would find any kind of living organisms that might have been there 3 or 4 billion years ago. So really the sky is the limit as to what we might discover. And I think we're in for some very exciting times.
And let's assume for a moment that they do find it. The next thing would be to determine whether or not it's life as we know it or life that has developed of its own accord, independent of what's happened on Earth. That would be the next big phase in researching this, I think.
Exactly, because if you really need to do genome sequencing to do this. It's not the kind of thing that Perseverance is equipped with, but so it would definitely be the province of testing samples in the laboratory back on Earth. But if you could do that and show that any life forms that are found on Mars have an origin independent of that on Earth, then you can be pretty sure that there's life everywhere the conditions are right, or microbial life anyway. If it turns out to have the same genetic origin as earthly life, then it's another really interesting development, because that tells us that one way or the other we're related to the Martians.
Yeah. And what would that do to the Drake equation?
Well, yeah, it probably makes the Drake equation a little bit more stringent. You know, if you do find that Martian life has an independent origin, then that actually, you know, it puts higher probabilities into the Drake equation than if it turns out to be related just to the earthly life. So yeah, it would change our view of ourselves and the possibilities of finding alien life.
Indeed. One of the other things that I've really enjoyed in regard to this successful deployment has been some of the social media activity. Lots of chitter-chatter about it, but some of the memes people have been putting out. You and I talked about one the other day where they dug up an old one from 1997 where it's got this panoramic photo of red Mars and rocks and everything and nothing but a McDonald's sign in the distance. I love that one. A bunch of Martian protesters telling Earthlings to buzz off, basically. They used a different word. But anyway, and then I saw another one where there were two aliens holding up a picture of a desolate planet in front of the rover's camera, screening a Martian city behind the picture. I thought that was a good one too. Yeah, people have been having a lot of fun with it. But, you know, that says to me that everyone's excited about this mission, excited about the success and the potential of it. I think when you start to make, you know, nice, clean, funny jokes about it like that, you're not having a crack. You're actually getting into the spirit of it, I think.
Yeah, very much so. That's right. It's great stuff.
It is indeed. We will watch with interest, of course, and we will certainly be here to tell you how things progress in the coming, 2 years is the life of the mission, isn't it, Fred? A couple of years?
Nominally, that's right, but you can bet your life it goes on for a lot longer than that.
Well,
assuming
look at the others.
Right. Yeah.
Yes, indeed. All right.
I mean, it's hard
You're
to...
listening...
Go on.
Sorry?
Go ahead. I was going to say...
No, I was just going to do my...
Yeah, Curiosity's been working for 9 years now. It's, you know,
incredible.
It's just, it seems like only yesterday that it went through its 7 minutes of terror. Yeah.
Yeah. It should have been called Perseverance by the sound of it.
Yes, it should, yeah.
And then this one, which was jealous, could have been called Animosity. Sorry.
Ooh.
Couldn't help it.
Ooh.
Time for a break. You're listening to the Space Nuts podcast with Andrew Dunkley and Fred Watson.
Space Nuts.
This is the Space Nuts podcast with Andrew Dunkley and, of course, Fred Watson, professor at large, or astronomer at large, but he's also a professor. But he's not a large professor. He's fit and healthy, as a matter of fact. Now, before we get back to our show and the next topic, just again, a shout out and thanks to our patrons who are signing up in ones and twos. But that's great. Thank you for putting a little bit of money aside to help the podcast and continue on. You can sign up for as little, or they put the price up for it, $4.50 a month, which is still, you know, not a massive amount of money, but $4.50 a month, or if you want to pay for a year in advance, which a few people have done, you can do that. You can do it through patreon.com/spacenuts. You can do it through Acast, or you can do it through Supercast. All the details are on our website. If you want to do it, it's purely voluntary at spacenutspodcast.com. Now, Fred, we have talked about the Gaia mission, the Gaia Observatory before, and what it's trying to achieve, but some new data from the Gaia Space Observatory has given astronomers a bit more of an inkling into what's happening with binary star systems. In fact, it looks like they've just released this incredible atlas of star systems that are being studied by Gaia. This sounds very exciting indeed.
It is actually. It's a slightly esoteric because it's the stuff of astronomy is binary stars, and well, just to recap on Gaia. Gaia is a space observatory, as you've said. It's run by the European Space Agency, and its mission is the very accurate determination of star positions over time. So not only do you get a snapshot at any given time of the exact positions of stars down to levels of micro arc seconds, which are, you know, on really unbelievable to a ground-based astronomer, where the atmosphere smears everything out to within 2 or 3 arc seconds. So its mission is to measure those positions. But of course, when you observe over time, you can see how stars move, how they drift through space, and that's what's allowed this new catalogue of binary stars. What are binary stars? They're stars that are connected by gravity, a pair of stars that are in orbit around their common centre of gravity, rather than just what you might call a double star, and amateur astronomers are very familiar with double stars. They're stars that look like a pair, but sometimes, one is 1,000 light years behind the other, because they may well be what are called optical double stars, where they just look as though they're together, but they're actually a line of sight accident.
Hello, Gregory.
Yes, yeah, that's right. Sorry, he's in the distance. I've got the door open. That's why, just to let a bit more light in. Anyway, astronomers are interested in binary stars because the thinking is that when you come to sun-like stars like the sun, about half of all sun-like stars should be in binary pairs. And that's really a very interesting statistic, because the catalogues of binary stars until now have been much smaller. I've been slightly involved with this kind of thing, but from a different perspective. When we were doing the RAVE experiment, the radial velocity experiment, one of the ways of detecting binary stars is to look for the changing velocities of stars as they orbit around one another. They're ones that you don't see as two separate stars. All you can tell is that there's two because the spectrum of the pair actually combines. And we found, I don't know how many it was a few dozen, I think, from the RAVE catalogue. A previous space astrometry observatory, and astrometry is the science of accurately measuring the positions of stars. In fact, Gaia's predecessor in many ways was called Hipparchus. I remember, I think it was 82, I was at a meeting where we were planning what Hipparchus might do, and now it's long gone and there's a super duper replacement with Gaia. But Hipparchus had a catalogue of something like 200 binaries from its data catalogue, whereas the Gaia sample now, they've just produced this catalogue of fairly widely separated binary stars within 3,000 light years of Earth, and they've got 1.3 million of them. So it's a much, much bigger catalogue. And of course, that actually allows you to do all kinds of statistics, because binaries aren't just sun-like stars. Many of them are white dwarf stars. Sometimes you've got a white dwarf star with a normal star companion. White dwarfs are what our sun will end up as in about 4 billion, 5 billion years' time. Yeah. All of that stuff falls into the catalogue of all these stars. So, how have they done it? Well, what they've done is it's been really quite clever. They've been looking specifically for binary stars that are relatively widely separated, so it takes them a long time to make one orbit around each other. And that's a bit difficult to measure with the kind of equipment, certainly, that we're using with RAVE. But with Gaia, what you can do is you can look at the motion through space of all the stars, and you can essentially, you're not just looking for stars that are close together in the sky. You're looking for stars that have they're close together, but they also have a common motion through the sky. So, and you can also, the other thing you can do is because Gaia can measure the distances of stars, you can check out that they're both at the same distance. So those are the parameters. You've got a pair of stars. They check out to be at the same distance from the solar system, and they are moving together the same direction in space. That tells you that you've got a real binary pair. And so, Gaia is essentially, essentially doing this work, and has produced this catalogue Actually, some of the people involved are people I know because they were involved with the RAVE program. Hans Walter Rix of the Max Planck Institute for Astronomy in Heidelberg, he's one of them. They have looked for binary stars that are separated by 10 times the distance between the Earth and the Sun, or 10 or more times. These are the sort of widely spaced ones, and what you get is something like, I think in their measurements they've actually measured that 25% of all Sun-like stars have a binary companion at separations more than about, actually these are quite distant, more than about 30 times the Earth's distance from the Sun, which is more or less the same distance from the Sun to Pluto.
Oh, okay.
And he said it's really interesting, the distribution peaks at a separation of 30 or 50 astronomical units, 30 or 50 times the distance to the Sun. That's really quite a curious phenomenon to find what distance you have the most of these pairs, and it must tell us something about the evolution of binary stars.
Well, we've talked before about our Sun having had a partner at some stage, whether or not it was a binary or if it was just I think we have referred to it as a binary, and it's drifted off somewhere. Just imagine, though, if it sort of was at the distance of Pluto, what would our solar system be like then? I mean, when you look at the Sun from Pluto, it's not very big, but if there was another one around that region, things would be very different, wouldn't they?
That's exactly right. They would. It is absolutely right that it may well be that the Sun had a companion back in the early history of the solar system, 4.6 billion years ago, that has now drifted off. That's now become freed from the gravitational attraction of the pair. And this plays into one of the things that has been discovered from this new catalogue, and I'm quoting one of the authors here. It's not Hans Walter, I can't remember which one it is, but let me just quote. This comes directly from the authors of the work. One thing we found that is cool, we discovered this with Gaia, but we can now study it better with the new sample, is that binaries like to be identical twins. So they're stars that are very, very similar in mass. Many binary star pairs are similar in mass. So if you've got one Sun-like star, you've got another Sun-like stars. And he says that is really weird because most of them are separated by hundreds or thousands of astronomical units, one astronomical unit being the distance of the Earth to the Sun. So they are so far apart that by conventional star formation theories, their masses should be random. But the data tells a different story. They know something about their companions' masses. And the implication is that they formed much closer together, in some sort of process that tended to equalize their masses and then migrated apart. Yeah. Maybe because of interactions with other stars. Remember that the Sun and most of the stars that we know actually are formed in clusters. So they, like the Pleiades, the seven sisters, that's actually got 200 stars in it or thereabouts. It's about 10 million years old, and those stars are typical of the kind of environment in which the Sun formed. Migrating apart is basically what happens, and that looks as though that is how the Sun lost its sibling, wherever it may be. Yeah.
So now that they've created this catalogue, this 3D catalogue of binary stars and systems, as you said, 1.3 million of them within 3,000 light years of Earth, what are they going to do with it? What will it be useful for?
Well, the sort of thing that we've been talking about, discovering what the conditions were like when these objects were formed. So that very thing, and it's actually Karim El-Badri, who's the author who I just quoted there, the very thing that he was saying, that the normal star formation theories tells you that the masses of stars should be random. But here you've got these widely separated pairs that are identical. So that immediately starts people looking back at their theories of star formation, the way stars form in clusters. That's the kind of thing that happens when you've got a really nice and large catalogue of any different class of object, whether it's quasars or galaxies or whatever. A large catalogue of samples lets you see the trends within it, and that's basically that they're further apart than you expect them to be. And it also lets you find the oddballs as well. That's one of the other things that catalogues do.
Yeah.
And so
I think Gaia spotted us.
Yeah, probably. These two strange stars are 500 kilometers or 350 kilometers apart.
Yep.
And they talk to each other every week. Well, that's strange.
Yeah. And of course, so typically astronomical, the creation of this catalogue and these discoveries has just created so many more questions.
Yes, exactly.
Which often happens in astronomy. So there'll be more to learn as, I suppose, people unravel the information that's been collated so brilliantly by Gaia. You're listening to the Space Nuts podcast, episode 241, with Andrew Dunkley and Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Welcome back. This is Space Nuts, the podcast. We talk about astronomy and space science and all sorts of other stuff here on the podcast. And, good to have your company. Thanks for listening to us and supporting us on whatever platform you listen via, whether it's YouTube, where we can also be seen. That's always a worry. But anyway, that's the way it is. Or you can listen through Apple Podcasts, Google Podcasts, Stitcher. Oh, the list goes on. But whichever platform you use, thank you for supporting the Space Nuts podcast. We appreciate it. And we love your feedback. And Fred, we've got some questions from the audience. And the first one's an audio question, and it's related to the recent Australian Open Tennis Championships. So,
hello, Andrew and Fred. This is Judd from Sydney. Love listening to your podcast every week. My wife and I love it. Thank you so much. We also love the tennis, and we've been watching a lot of the Australian Open over the past week. And I have a tennis astronomy question for you. I notice when we're watching daytime matches and the shadows creep across the court during the play, it's a bit distracting for the players, and they must have to work very hard at precisely aligning the courts so that the shadow lines up perfectly with the lines of the court. And it just occurred to me, like, what would happen if the Earth's axis of rotation shifts slightly? That would throw off the alignment of the shadows, wouldn't it? And I wondered how often that has happened, or does it ever happen, and why does it happen? And how we know that. And, yeah, it must throw things off a lot in the tennis, but it must also affect ancient civilizations whose calendars, were so precisely coordinated with the sun's path. I've been to Machu Picchu in Peru and seen how these temples were built, where they precisely lined up things so that you could only see the sun through certain paths at one day of the year at a certain time. So, yeah, I just wondered how the Earth's axis changes and affects things like that. Thank you.
Okay. Interesting question. And shadows can be very, very unpopular in sport. Games like golf, for example, shadows can affect your capacity to line up a putt, especially the shadows of trees. Although, Fred, I've had a couple of occasions where the ball has stopped on the shadow of the flagstick, and it's given me a straight line to the hole, and I've found that to be an advantage. It's very rare that it happens that way, but it has happened a couple of times. But more often than not, shadows are a big hindrance in sport. And I can imagine in tennis, when you're going from being in bright light to shadow, trying to track that ball and hit it, could be a real pain, because the ball would be in the light and it'd be bright yellow, and then suddenly it hits the shadow, and it could throw you off. So he was, just to reiterate, he was wondering about changes in the Earth's axis affecting shadows in terms of the alignment of these complexes. I suppose they have to consider those sorts of things when they build stadiums around the world, to take into account the local perspective in terms of seasonal sun positions.
That's absolutely right. They do, and so a lot of these, facilities are aligned north, south, or east, west, or whatever. But let me just go back to the first part of Judd's question, because a bit of thought will show you that it doesn't really matter where the sun is and what the Earth's axis is doing. The shadow of the stadium will, if it starts off parallel to the court and the marking lines of the court, it will always be like that, because what you're talking about there is only the relationship between the court and its markings and the structure that is supporting the roof of the stadium. So if the roof is parallel to the markings on the court, then its shadow is always going to be parallel to the markings on the court. And it doesn't really matter where the sun is, that parallelism will always be maintained.
Okay.
But Judd's right that things do change. The Earth's axis is actually very, very stable. There are very slight changes, ranging from changes that amount to a few tens of meters at the North Pole, which is trivial, really. The biggest change, though, is one that doesn't really affect shadows that much, and that's why things still work at Machu Picchu. I've been there too, and to many other archaeoastronomy sites in Peru. That is the precession of the Earth's axis. So by precession, I mean, and it's easiest to imagine it with a spinning top. A spinning top is rotating on its axis, but it's also got this wobble. And if you think about it, the axis traces a circle out, and the Earth does exactly the same thing. It has this wobble. It takes the Earth's axis 26,000 years to go around once. It's not a new discovery. The ancient Greeks knew about this, because you can sort of work it out from the way the constellations change. It's called the precession of the equinoxes, and that's because that's what happens. The equinoxes change along the celestial sphere. So while the sun doesn't really change its positions, the stars do, in terms of the way that you see them. And that, for example, has allowed, in ancient times, people much further north than they can today, they could see the Southern Cross, whereas now it's invisible because precession has taken it below the horizon. And so and we see the effect of it too in things like the alignment of the pyramids, the ones that were built 4,000 or so years ago, often aligned by the stars, and those star positions have changed with respect to the Earth's equator because of this precession phenomenon. So yes, there are changes, and yes, they do affect our view of ancient astronomers, the science of archaeoastronomy, which is a very, very well developed field, and of course takes all these things completely into account. So yeah, great question, Judd, and it all started on a tennis court, which is great. And look, I agree with you, Andrew. I've looked at these matches and think, how on earth do the players cope with the fact that it's in bright sunlight for half the flight of the ball and in shadow for the rest of it? It must be very, very challenging.
Yes, I've seen some of the professionals on the US PGA Tour trying to putt through the dappled shadows of the leaves and branches of trees, and it really messes up your ability to read the putt, because for those who are non-golfers who don't really get it, it's not a flat surface. It's not always a straight line. In fact, most putts aren't. You've got to allow for the ball to curve with the contours of the green, and that's why they get down on their haunches and look along the line of the putt to see where the slope is, so they can work out what to aim at to make it curve at the right speed to get into the hole. And if there's shadows on the green, it's much, much harder because it hides things. It disturbs your perspective and makes it much more difficult to define. But and I'm
gives
sure
you a good excuse though when you miss the whole.
Oh, I don't need shadows. Got plenty of excuses. Actually, while we're talking about golf, last weekend, because we were hosting a New South Wales event at our course, I couldn't play in my local course. So I played a course I haven't played before, which is just up the road at a little town called Narromine. And it's got sand greens. Now, I haven't played on sand greens for 20 odd years, and it's a completely different ball game. And yeah, that was fun. I did actually play quite well, but yeah, it took me a few holes to get the hang of it because it's so different compared to putting on grass. But yeah, shadows aren't really a factor on sand greens because they're black. Because they're oil based, so the sand doesn't blow away.
Oh, I didn't know that.
Not that big a deal. Yeah, but thank you, Judd, for the question, and I hope that resolved your query. Let's move on to our next question. This comes from Matt Hughes in Gisborne in Victoria. My question relates to the Lagrange points, particularly the L2 point. I understand the Chinese have a satellite retransmitting signals from the dark side of the moon. The Russians have a satellite there, and the James Webb Telescope will be there later this year. I'm wondering how big the Lagrange points are, particularly L2. Is there an ideal position where the desired gravitational effect is best? I understand L2 is unstable. What does that mean? It's been listening to Space Nuts. That's what that means. Are objects in the L2 monitored to make sure they don't hit each other? Is there an international treaty? Thank you both for a very informative and enjoyable podcast. All the best for your time. Matt Hughes. Lots of Lagrange type questions built into that one. Fred, where do you want to start?
Let's just start with the Lagrange points themselves, and so people know what they are. So if you have two objects, one in orbit around the other, and let's start, for example, with the Sun and the Earth, there are five stable points which feel the gravity of both of those objects, but also are affected by the fact that one is rotating around the other. And they were discovered by Monsieur Lagrange back in, I think it's the end of the 18th century. I used to do a talk on this, so I should know these dates, but I can't remember. If I remember rightly, he's the guy, yes, it must have been the end of the 18th century, because he very nearly got hauled off to the guillotine. Is that right? Was that Lagrange, or was that might have been somebody else? I need to check it before I start going on about these stories. One very famous astronomer of the time, very nearly, in the French Revolution, lost his head. Anyway, Monsieur Lagrange worked out that there are these five stable points, and the easiest one to get your head around is what we call L1, the first Lagrange point. And that's the balance point between the Earth and the Sun, if you're talking about the Earth-Sun Lagrange points. It's where the Earth's gravity is equalised by the Sun's gravity. And it's not too far from the Earth, because of course the Earth is much smaller than the Sun. But the other ones are a lot harder to get your head around because they're quite counterintuitive. But remember, you have to take into account the fact that you're in a rotating frame of reference, so there are other accelerations involved other than gravity. So the L2 point is the same distance from the Earth as the L1 point is, but it's on the other side of the Earth. So you're there, then you've got this situation of the Sun, the Earth, and the L2 point. There's a stable point beyond the Earth. The L3 point is on the opposite side of the Earth's orbit from where the Earth is, and that's one that tends not to be used for anything much. And then the two L4 and L5 points, and I always get them the wrong way around. I think L4 is the leading one and L5 is the trailing one. They're in the Earth's orbit, but 60 degrees ahead of and behind it. And the thing about these points is they're all gravitationally stable at some level. And let me go straight to one of Matt's questions. I understand L2 point is unstable. What does that mean? In fact, they all are slightly. It means that if you put an object there, yes, they're feeling this gravitational null, but they're in a peculiar, what you might call gravitational well, that sort of has, ways of leaking out. So if you place a spacecraft at one of these Lagrange points, you do have to keep it there. It's what's called station keeping by the spacecraft engineers. So they're all a little bit unstable. Now, let me go back to the first part of Matt's question. I understand the Chinese have a satellite retransmitting signals from the dark side of the moon. The Russians have a satellite there, and the James Webb Telescope will be there later this year. And now there's some confusion there because the Chinese satellite, I can't remember its name in Chinese, but it means Magpie Bridge. That's the translation. And it's exactly right that they have a satellite at the L2 point of the Earth-Moon system, not the Sun-Earth system. So this thing is on the far side of the moon, but like all spacecraft which are dealing with L2 or any of the Lagrange points, it's not actually at the point, it's in an orbit around it. And I know that sounds completely screwy, that you can put something in orbit around an imaginary point where there's no planet or anything, but that's how these things work. So the Magpie Bridge satellite is in orbit around the L2, the Earth-Moon L2 point, and it's far enough from that point that you can actually see it on the other side of the moon. So it not only sees the Earth, it also sees the far side of the moon. The James Webb Telescope will actually be at the Earth-Sun L2 point. So the reason for that is that it's always going to be shaded by the light from the light of the sun, or the heat radiation of the sun, by the Earth itself. Yeah. The Earth is going to be in the way. It will still have heat shields.
So the sun will be there, we'll be here, and James Webb will be over there. Is that right?
Exactly. Yeah. That's right. Well, probably, yeah. I couldn't see what you were doing there because I'm looking at a different page.
I'm using my head as Earth.
Oh, let me see that again.
All right. I'm Earth. You are the sun. And the James Webb is that cricket trophy.
Yeah, that's right.
Now it's the
trophy in the back. Yeah. And yes, when you look closely, you can see that cricket trophy is in orbit around an imaginary point behind your head. How big are the Lagrange points? Well, they're points, but they do have this sort of sphere of influence that's quite large. As I said, they're at the bottom of a peculiarly shaped gravitational well. And what that means, because nobody actually puts a spacecraft exactly at the L2 point, you always put it kind of in orbit around it. It's not quite such a crowded area as Matt has inferred. Our objects in the L2 point monitor to make sure they don't hit each other. Well, they are. And yes, there are agreements about things like that. These international agreements are a little bit woolly in some cases on things of that kind of level. But hopefully there'll never be a collision. It's a bit like the way, I think what happens is a bit like the way positions in geostationary orbit are allocated. You kind of buy your space. In fact, it's a square or a cubic volume of space that you buy, or you claim, or whatever, when you put a geostationary satellite up. And I'm sure there are similar deals which are done with the Lagrange points. And finally, just to tie up the loose end, the L4 and L5 points are important. They're the ones that are in the same orbit as a planet going around the sun, because certainly in the case of Jupiter, there are 9,000 asteroids that are that orbit around the L4 and L5 points, and we call them the Trojan asteroids. There's, I think Neptune also has some Trojans, nowhere near as many. And I think Earth might even have one or two as well. There's been some observations of asteroids that look as though they are in orbit around the L4 and I think it's L4, one of the two, of the Earth's orbit. So interesting stuff. And a bit unexpected that there should be these stable points in space, but they're being used, as we've said, by the space mission, space agencies, and the commercial space world as well.
Okay, there you go, Matt. Thank you for the question. And just in regard to your thought about his impending death, it was actually to do with the reign of terror during the French Revolution. Lagrange had been invited to Paris as a scientist. And around that time, during this reign of terror, there had been a decree ordering all foreigners to leave France. He was given a special exemption and allowed to stay, and so he was not sent to the guillotine, as was one particular scientist named Lavoisier, I think.
Oh, Lavoisier, yes.
And
right.
27 other tax farmers who were arrested and sentenced to death and guillotined on the afternoon of the trial. Lagrange said of the death of Lavoisier, it only took a moment to cause his head to fall, and 100 years will not suffice to produce its like. So
there you go.
He didn't take too well to that, but he did survive under those trying circumstances.
So was the right guy that I was thinking of, yeah. That's
yes,
good.
Indeed. Thanks again, Matt. Thanks also to Judd for the questions. Thanks, everybody, for listening. Don't forget, if you do have a question for us, go to our website, spacenutspodcast.com. You can send it through us to us in text form using the email interface, or you can send us an audio question. We do love those. Don't forget, in both cases, though, to tell us who you are and where you're from. We love to hear from your voices, but we also like to know where you're from. Being an international platform as Space Nuts has, it's a not just international, it's universal. It's a universal platform that we offer. But thank you for your contributions, and we'll look forward to some more questions very soon. Fred brings us to the end of another episode. Thank you, sir.
Great pleasure. Good to talk, and there'll be no doubt many more things to talk about next time, which I look forward to.
Yes, indeed. Thanks, Fred. Professor Fred Watson, astronomer at large, part of the Space Nuts team, and thanks again to Hugh back in the studio, who puts all the nuts and bolts on it and takes parts from my Honda Jazz to keep it all together. And from me, Andrew Dunkley, thanks as always. See you next time. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.